Hello everyone, welcome back to my YouTube channel. So today I'll be discussing a topic from the subject design and analysis of algorithm whose subject code is 21CS42. So as you all know, my name is Likith. So let's get started. So the topic of today's video is graph searching algorithms. So graph search or graph traversal algorithms explore a graph for general discovery or explicit search. They will try to visit as much of the graph as they can reach, but there is no expectation that the paths they explore are computationally optimal. Graph search algorithms are usually used as core component of other algorithms. So there are two types of graph search algorithms. The first one being depth first search and breadth first search. So let's move on with depth first search. Depth first search starts visiting vertices of a graph at an arbitrary vertex by marking it as having been visited. On each iteration, the algorithm proceeds to an unvisited vertex that is adjacent to the one it is currently in. This process continues until a dead end, a vertex with no adjacent unvisited vertices, is encountered. At a dead end, the algorithm backs up one edge to the vertex it came from and tries to continue visiting unvisited vertices from there. The algorithm eventually halts after backing up to the starting vertex, with the latter being a dead end. By then, all the vertices in the same connected component as the starting vertex have been visited. If unvisited vertices still remain, the depth first search must be restarted at any one of them. It is convenient to use a stack to track the operation of depth first search. We push a vertex onto the stack when the vertex is reached for the first time. That is, the visit of the vertex starts, and we pop a vertex off the stack when it becomes a dead end. That is, the visit of the vertex ends. So now let's move on with the algorithm of depth first search. So let's start. DFS of G implements a depth first search traversal of a given graph. The input being graph G is equal to V comma E. Output graph G with its vertices marked with consecutive integers in the order of they have been first visited by the DFS traversal. Mark each vertex in the set of vertices with 0 as a mark of being unvisited. Then initialize count to 0. Create a for loop for each vertex V in the set of vertices capital V so that if V is marked with 0, then perform DFS of small v. Then close the for loop and perform DFS of the particular vertex. Visits recursively all the unvisited vertices connected to vertex V by path and numbers them in the order they are encountered via the global variable count. Then count tends to count plus 1. Mark V with count. For each vertex, W in capitals V, that is set of vertices that is adjacent to the particular vertex, do. If W is marked with 0, then perform DFS of W. For the adjacency matrix representation, the traversal time is theta of mod V square, and for the adjacency list representation, it is then theta mod V plus mod E, where mod B and mod E are the number of graphs, vertices, and edges respectively. So now let's move on to breadth first search. The breadth first search, it proceeds in a concentric manner by visiting first all the vertices that are adjacent to a starting vertex, then all the unvisited vertices, two edges apart from it, and so on until all the vertices in the same connected component as the starting vertex are visited. If there still remain unvisited vertices, the algorithm has to be restarted. at an arbitrary vertex of another connected graph, at another connected component of the graph. It is convenient to use a queue to trace the operation of a breadth first search. So now let's move on to the algorithm of the breadth first search. So we'll start. BFS of G. It implements a breadth first search traversal of a given graph. The input being a graph G with V, E, that is vertices and edges. Output graph G with its vertices marked with consecutive integers in the order they have been first visited by the breadth first search traversal. Mark each vertex in the set of vertices V with 0 as a mark of being unvisited. Then initialize the count to 0 for each vertex. For each vertex, small v, a particular vertex in the set of vertices V, perform if V is marked with 0, then perform BFS of V, then close the for loop, then perform BFS of that particular vertex. Then visits recursively all the unvisited vertices connected to the vertex V by a path and assign them numbers in the order they are visited, that is via a global variable count. Then count tends to count plus 1. Mark V with count and initialize a queue with V. While the queue is not empty, perform for each vertex W in a set of vertices V adjacent to the front vertex. Perform if V is marked with 0, initialize count, that is count tends to count plus 1. Mark W with count, add W to the queue, then close the for loop, then remove the front vertex from the queue. Breadth first search has the same efficiency as the depth first search. It is then theta mod V square for adjacency matrix representation and theta mod V plus mod E for the adjacency list representation. So this ends my presentation. Thanks for watching, and I've made videos on different topics, so please check those out. Thanks for watching.